properties. Remember, we talked about two preparation methods, and these are the important and the methods which will be asked, okay, in which out of which Williamson synthesis is very important one. Okay. So CO bond in ethers are polar because oxygen is electronegative, carbon is electropositive. So if we say it is C2H5O C2H5, this oxygen will have two lone pairs. Now, because there will be two lone pairs, it will actually be tetrahedral geometry, although its shape will be bent like water. So one lone pair, another lone pair, and then you have here C2H5 and another C2H5. Because this is electronegative, carbon is electropositive, that's why this is polar. So, and because the structure is tetrahedral, there will be net dipole moment. Okay? It will not get cancelled. It is not linear. So net dipole moment will be from positive to negative. It will be there. So the weak polarity of ethers does not appreciably affect their bonding boiling points, which are comparable to those the alkanes. Okay, so if the molecular masses are same, and this will help you to answer quite a few questions where you will have to arrange the ethers and hydrocarbons along with, okay, in the increasing or decreasing order of boiling point. So there is not much difference if we are talking about similar molecular masses. Okay? Similar molar masses, similar boiling points. So this dipole moment is very, very weak. The large difference in boiling points of alcohols and ethers is due to because in alcohols we have significant hydrogen bonding. So this is hydrocarbon 309.1 and this is ethoxyethane ether. Not much difference in boiling point. But if this is alcohol 390, the boiling point increased significantly due to hydrogen bonding. Okay. So just memorize at least these 2 points. If you compare these two, ether has slightly less boiling point. Okay, ether has slightly less boiling point. The reason significantly is that first of all, it has 4 carbon atoms. In N-pentane, we have 5 carbon atoms. Moreover, this structure is linear. This structure is bent. So linear structure will have more contact surface area as compared to bent. So linear will be better symmetrically arranged as compared to ethers. So that's why slightly boiling point is higher in this case. So good evening. The miscibility of ethers with water resembles those of alcohols of the same molecular mass. So both ethoxyethane and butanol are miscible to almost the same extent, that is 7.5 and 9 grams per 100 ml of water, respectively, while pentane is essentially immiscible with water. And the reason is very simple because there is some dipole moment, so it is polar. Polar dissolves polar. So ethoxyethane is miscible in water, alcohol is miscible in water, but N-pentane or pentane, this is non-polar. That's why immiscible in water. Hydrogen bonding, another reason in case of ethoxyethane and water, there will be hydrogen bonding. In case of alcohol and water, there will be hydrogen bonding. If I'm showing this one as ether, this is ether. Okay. Say it is C2H5O, C2H5, and you have H2O. So this hydrogen and oxygen will have hydrogen bond because this has one lone pair, and there are two lone pairs, so there are two possibilities. Similarly with alcohol, both will be miscible. Now the chemical properties, and these are very important. Reactions are of various types. So reactions with ethereal oxygen means oxygen present in the ether. There are few types of reaction. Then reactions involving cleavage of CO bond. For example, if it is CH3, CH2O, CH3, then breakage of CO bond. These are CO bonds. So then there are different types of reactions. Then reactions of alkyl group, in that we have halogenation, and ring substitution also we have there halogenation and also Friedel-Crafts reaction and nitration. These are the similar ones you have already done. So action of air, formation of peroxide. This is something different reaction, not related to what types I just explained. Okay. So here we have the ether, and it reacts with oxygen in presence of light. And one ethoxyethyl hydroperoxide is formed. You need to write the structure and name of the product, because if you don't memorize this, you will not be able to write this reaction if it appears. So ethers do react with atmospheric oxygen in presence of light, and they produce hydroperoxide. Why hydroperoxide? Because it has peroxide linkage. Peroxide linkage here. Just remember the reaction, and similar reaction you need to write if it is not ethoxyethane. Suppose it is methoxymethane, similar reaction. Peroxides are formed. Action with concentrated acids. So we have concentrated H2SO4, concentrated HCl. Oxonium salts are formed. Oxonium salts means oxygen has a positive charge. Oxonium ion means, if you see anywhere oxonium ion, it means oxygen has positive charge in ionic form. So here this is oxonium ion, here this is oxonium ion. Write down the reaction and memorize. Reactions are very much similar. In case of H2SO4, it will be H plus HSO4 minus. So this HSO4 minus will be the anion. In case of HCl, H plus Cl minus. So this chlorine is anion. H plus in both cases attaches to oxygen, because the basically the arrow, if you show the mechanism, the arrow will be reversed because the electrons will attack on this proton. Reaction with Lewis acids, formation of coordination complexes. Coordination complexes, more about it we will be talking about in chapter, coordination compound. So here these are the ethers, and you know that these are Lewis acids. BF3 is Lewis acid because it has 6 electrons in outermost shell. So it is looking for electron. So the species which are looking for electrons or accept the electrons are acids, Lewis acids. So the oxygen of the ether provides its electrons to boron. So that's why coordinate bond is formed. This is coordinate bond. Coordinate bond is just similar to covalent bond. The only difference is the electrons are provided only by only one species. Now here again ether and Grignard reagent. In Grignard reagent, Mgx is positive and R is negative. So the oxygen electrons actually attack on positive Mgx. Here magnesium is willing to get electron. So that's why a coordinate bond is again formed here. Two coordinate bonds are formed. Magnesium gains 2 electron here, two bonds here, two pairs of oxygen, one each from one molecule. So here again we have Mg here. So this one gets attached here and this one again gets attached here. We have two. So you can understand it in a different way. If I write it like CH3, CH2 whole twice, or another one. So one pair gets attached, another pair gets attached. Okay. Now Mg has X attached to it. So that is anyway there attached to this one. And R remains attached to magnesium. So RMgX remains as it is in this case. Only the lone pairs attack on magnesium because magnesium is positively charged here in this case. Okay, I'll show the previous slide after this one. So here what's happening? Again, oxygen of the ether is attacking. In this case, oxygen of ether attacked on boron, formed the coordinate bond. And in this case also, oxygen of the ether attacked on magnesium. This is the previous slide. Okay. Here also, if you see, I have shown oxygen attacked on proton, electrons of oxygen attacked on proton. So ethereal oxygen is attacking on other reagent. Ethereal oxygen means oxygen of ether. Then reactions involving cleavage of CO bond. First one, cleavage by halogen acids, HI, HCl, etc. So you have ether here and you have halogen acid at around 100 degrees Celsius, 373 K means 100 degrees Celsius. You get alcohol as well as halide. Now, if excess acid is used, so sometimes you will get this reaction written as HI is in excess. Then what will happen? The alcohol which is produced again reacts with HX. It gets ample time for alcohol to react with the halogen acid. at the same temperature, and it produces hal- hydrocarbons. Okay, hydrocarbons means alkyl halides. And this is something you know, preparation method of haloalkanes from alcohols. So you need to remember both. In this case, if the halogen acid is in just sufficient amount, then alcohol and haloalkane will be produced. But if the halogen acid is in excess, then only halogen acid will be only haloalkane will be produced along with water. So if this one is, I'm talking about this alcohol, if it is CH3 CH2OH, it will again react with HI at the same temperature and will produce CH3 CH2I and H2O. So effectively you have only haloalkane, that is ethyl iodide in this case, only that product. This question is very important. You need to understand the difference. Halogen acids just in sufficient amount or nothing is written there. Then alcohol and haloalkanes will be produced. If halogen acid is in excess, only haloalkane will be produced. Two reactions will occur. Now, cleavage of unsymmetrical alkyl ethers, where it will get cleaved. So remember, when we talked about here, in this case, uh, it was easy that to understand that whether the cleavage is this CO bond or this CO bond, one gets attached with iodine, one gets attached with H. So the one which gets attached with H, for example, cleavage is here. This is cleavage. So this part got connected with iodine, and this part, because it has oxygen which has lone pair, so lone pair will attack on H plus. So it was easy to understand that ethyl alcohol and ethyl iodide will be produced. But suppose it is not symmetrical. Both sides of oxygen have different. In this case, I have methyl and ethyl both. Then what will be produced? In that case, you just need to remember the rule. The smaller one will be halide. If the smaller one is the halide, means the cleavage will be from that side only. Cleavage will be from a smaller alkyl group. Just remember that rule. The other one will have, this is H plus I minus. This electron will attack on positive. Okay. Iodine will get attached to carbon, electropositive carbon. Now, if however one of the alkyl groups is tertiary group, the alkyl halide is formed from the tertiary alkyl group. So I'm talking about the same reactions, same conditions, 373 Kelvin. But here the difference is you have this one, but the bigger one is a tertiary. Then tertiary will form the alkyl halide. Who will tell me the reason? Why? Who is going to tell me the reason? Okay, Ashi, Vanna, Mehak. Yes, correct. Vanna, yes, SN1 mechanism, correct. Arohi, yes, correct. Okay. Because now SN1 mechanism carbocation, tertiary carbocation will be more stable. So tertiary carbocation will be more stable. Hence, cleavage will take place from here. And we will get CH3, CH3, CH3 plus and OCH3 minus. Now this is negative. So negative will attack the positive carbocation and this oxygen will attack H plus. Okay, so why this was not the case in previous case? Yes, correct. So who will tell me why in this case, what was the reason? Why this bond got broken here? Yes, Arohi, correct. But tell me the reason also. Your observation is correct, but tell me the reason also. Yes, yeah, Shashwat, that is something I told you to remember. That helps. For example, I said that smaller the group, cleavage will take place from that side. But with that, there is a condition that if there is a tertiary group, then cleavage will take from tertiary group side. Okay. Now my question is, why from the smaller group side? For example, in this case, why from CS3 group side? So I'm getting answer from Arohi, Ashi, for example, uh, SN2 mechanism, SN2 mechanism. Mehak, okay, yes, correct. Um, Good. Arohi, yes, now correct. Ashi, correct. Ahan, correct. It is because in SN2 mechanism, the hindrance plays the role. And with the smaller group, there is less hindrance. Okay, larger the group, there will be more hindrance. Smaller the group, less hindrance. Preeta, correct. Okay, so that is the reason. But if it is tertiary, then altogether the mechanism will change. It will be SN1 in that case, and tertiary carbocation will be more stable. So you need to remember these differences. Actually, questions will appear from all these points where there are some exception type of things. Although these are not exceptions, but different things. Okay, cleavage of alkyl aryl, that is phenolic ether. So this is again ether, but here we have one side, one arm as phenol. In this case, cleavage is taking place again from the smaller group. CH3 is smaller, so cleavage takes place from that side. Again, the hindrance part. So it is similar to that one. Cleavage of benzyl alkyl ethers. Now you have methyl and this group is benzyl. It is not benzene. Okay? It is benzyl. Now that changes the mechanism. That changes the mechanism. We have H plus and I minus. Okay. So this oxygen will attack on the hydrogen. Okay. So if this attacks on hydrogen here, so hydrogen will get attached to it. Oxonium ion. I told you that if it is positive oxygen, it will be oxonium ion. So oxonium ion will be formed. Once this oxonium ion is formed, after that, what happens? This bond breaks. And this provides its electrons to this oxygen. Because oxygen has positive charge, it is unstable. And we get benzyl carbocation. Benzyl group has positive charge, benzyl carbocation. Along with this alcohol. This benzyl carbocation gains this remaining iodide and produces benzyl iodide. This mechanism itself is very important. Quite frequently it appears in exam. So write the mechanism of the reaction of benzylic ethers. Okay, benzylic ethers with halogen acids. So benzylic ethers with halogen acids, this is the mechanism. Mechanism of reaction of benzylic ethers with halogen acids. This is what you will write if you are asked about the mechanism. Previous slide was this one, Mehak. It is similar to the other one. In this case, cleavage will take place here. Next is cleavage of diaryl ethers. Diaryl ethers such as diphenyl ether are not cleaved by HI. So suppose you have C6H5O, C6H5, diphenyl ether. These are not cleaved by HI. This is because CO bonds have some double bond character due to resonance. So here also in this case, if you remember, this bond will have double bond character, so it will be difficult. This bond, partially double bond character, cleavage will take place from here. Okay. Here, this bond does not have double bond character. So that's why the reaction mechanism is different in this case from the previous one. This one difficult to break. But here, there is no such case. Okay. So this is because CO bonds have some double bond character due to resonance between lone pairs of electrons on the oxygen atom and carbon atom on the aryl groups directly bonded to oxygen atoms. Next is cleavage by sulfuric acid. So in this case, remember quite a few times you might need to write no reaction. Okay, there are questions which will ask you to write the product. Question will be like this. 373K, no reaction. Cleavage by sulfuric acid. Now, when we say sulfuric acid, so remember here we talked about halogen acids. Here we are talking about sulfuric acid. This reaction is also known as acidic hydration or acidic hydrolysis. Okay. So in this case, specifically whether cleavage is taking place from here or from here, H2O will act as H plus OH minus This oxygen will attack on hydrogen, so OH will be produced. This OH minus will attack on the CH3, CH2 plus. So again, alcohol will be produced. Two molecules of alcohol will be produced. If concentrated H2SO4 is used, so remember we are using dilute here. That's why reaction is with water. And that's why I said it is acidic hydrolysis. If concentrated H2SO4 is used, ethers form alcohol and ethyl hydrogen sulfates. So in this case, alcohol will be there, but ethyl hydrogen sulfate will also be produced. The reason is very simple because in this case, you will have H plus and HSO4 minus. So if cleavage takes place from here, these two electrons will attack on hydrogen and will form alcohol. And this negative part will attack on this carbon and will form ethyl hydrogen sulfate. This is OSO3H. It is actually HSO4 minus. Yeah. Because it is attached through O, that's why it is written as OSO3H. So reactions with dilute sulfuric acid, concentrated sulfuric acid are different. However, in both cases, alcohol will be formed. Dilute sulfuric acid only alcohol, and that is actually very good conversion method also. You will be using this one as conversion method from ethers to alcohols. So write down quite a few times so that you can recall it when we do conversion questions. Secondary and tertiary ethers, however, form alkenes with concentrated H2SO4. So with concentrated H2SO4, if we have here tertiary ethers, we will get alkenes. Remember, alcohol is anyway formed. It is H plus, HSO4 minus, alcohol. So methyl alcohol will be formed and cation will be attacked by the negative part. So here from here, what will happen? H will go from this side. So from here, hydrogen will move. Okay. So when hydrogen moves from here, double bond will be produced. Hydrogen can be removed from anyone because it is symmetrical cation. So from wherever hydrogen is removed, you will get the double bond there. Next is cleavage with phosphorus pentachloride, PCl5. It is similar reaction. Now you can remember that if you get alcohols reacted with PCl5, you get alkyl halides. If you get ethers reacted with PCl5, again you get alkyl halides. Okay, the reaction was similar. If you had just what is the difference in ether and alcohol? This part is H in case of if you have C2H5 OH means this is hydrogen part just instead of alkyl group you have hydrogen. That is the difference. Reaction is similar. In case of alcohol also you will get alkyl halide. In case of ethers also you will get alkyl halide. You will be using this one for conversion questions. Conversion of ethers to alkyl halides. Previous one was conversion of this one. Conversion of ethers to alcohols. This one is conversion of ethers to alkyl halide, PCl5, similar to alcohols. In all these cases, CO bond is being cleaved, means broken, being broken. Cleavage by acid chlorides or acyl chlorides. So you can get both words written here, either acid chloride or acyl chlorides. So you have acetyl chloride here. This is acyl group, but because it has two carbons, so acetyl chloride. It will be in presence of anhydrous zinc chloride, and this is sometimes indication. It will be given on the in the fill in the black type questions or complete the reaction type questions. So anhydrous zinc chloride will be written here. So it means this is cleavage by acid chlorides. Again, the reaction is very much similar. Leave it. The oxygen will have here the electrons, and carbon will have slightly positive charge. So slightly positive charge means chlorine will get attached to this carbon. So you will get ethyl chloride. And rest will be attached to the other part. This CO, CH3CO will be like this, CH3CO. It will be slightly polar. So this carbon will be positive, slightly positive. So the electron will actually attack on this carbon and will form ester, ethyl acetate. However, with anhydrides, so this is anhydride. Anhydride generic form is RCO whole twice O. This is general form of anhydrides. RCOCl is general form of acyl chlorides. So if it is anhydride, only esters will be formed. With similar reagents. Acyl and anhydride are similar reagents because both have RCO group. And you will see that in many cases, these will give same products. Whether I talk about acyl chloride or anhydride, both will give same products. But in case of ethers, there is difference. Both have RCO group. RCO group is here as well, and RCO group is here as well, whether it is acyl chloride or acid anhydride. But reactions are different. Two reactions are similar. I'm not saying same. That depending on the condition, the product will be different. Okay. So just understand, in this case, only ester. In this case, ester and alkyl halide. I'm going back just to tell you this one. Cleavage by sulfuric acid. Dilute sulfuric acid, only alcohol. Concentrated sulfuric acid, acid plus ethyl hydrogen sulfate. So with the sulfuric acid, there are two different types of reaction, different depending on dilute or concentrated with ethers. In one case, only alcohol. In other case, alcohol with alkyl hydrogen sulfate. Here also, reaction of ether with similar reagents, that is acyl chloride and acid anhydride. In case of acyl chloride, ester plus alkyl chloride. In case of acid anhydride, only esters. You need to remember all these points. Wherever there is slight difference, questions will appear. Most of the questions will be, or you can say that the chances of questions appearing from these sections higher. Reactions of alkyl groups means halogenation. And then we will be talking about halogenation again on the ring. So here we are talking about alkyl group. You have ether, you get it reacted with halogen chlorine in dark, monochlorination takes place. First step. Okay. But again, the same condition, I am not changing the condition. Okay. On the other carbon also, chlorine displaces hydrogen. Now see the IUPAC name. 1 dash dichloro diethyl ether. Both the carbons are treated as one. So this is one, this is two. This is 1 dash, this is 2 dash. This is how the IUPAC naming is done in ethers. In this region at 1 you have chlorine, in this region at 1 dash you have chlorine. So 1 dash dichloro, then diethyl ether. However, in presence of light and excess of chlorine, all the hydrogen atoms are substituted by chlorine atoms. There is no hydrogen at all. All hydrogens replaced by chlorine in presence of sunlight. And obviously you need to have excess of chlorine because all the chlorines will replace the hydrogens and will produce 10 HCl in this case. So excess of halogen required. Again, depending on the condition, the product is different. Important reaction. Halogenation of alkyl group, you have two reactions. Whether it is in dark, if it is in dark, only the hydrogen on the carbon which is attached to oxygen. Only on that carbon, one hydrogen will be displaced, okay, from both sides. But if it is sunlight and excess of halogen, then all the hydrogens will be displaced. Write down these reactions and make sure that you revise these reactions after the test today. You know there is a test today. Yeah. Next, ring substitution in aromatic ethers. So here also, Arohi H nu means energy. This energy, you know, in 11th we talked about E is equal to H nu. Yeah. This is actually the energy provided by sunlight. H nu. That is what we say that this is quantum energy of a photon. Ring substitution in aromatic ethers. So these are aromatic ethers. This is aryl part, this is alkyl part. Aryl part is there, that's why aromatic ether. Halogenation, we have bromine and we have an acid, acetic acid. Conditions you should remember. Para will be the major product. So halogenation in aromatic ethers is simpler. Ortho and para compounds will be produced, para will be major product. So that's why I said that these three, halogenation, alkylation, etc., you have done, or sulfonation. Yeah. So Friedel Craft, alkylation or acylation, similar reaction what you have done. For alkylation, you use Alkyl chloride, for acylation you use acyl chloride. You know that this is acyl group, RCO, acyl group. And again, similar one, ortho and para will be produced. In this case, methyl will get attached at ortho or para. Para will be major. So alkylation, because alkyl group. Here, acyl group will get attached on ortho or para. Para will be major. Conditions are very important. Anhydrous AlCl3 in CS2, anhydrous AlCl3 in CS2. For Friedel-Crafts reaction, this is actually an indication. Although FeCl3 might be written there, okay, but mostly you will get anhydrous AlCl3 in CS2. So this gives you a hint that we are talking about Friedel-Crafts alkylation, and specifically it will be important when we will do questions related to that. When A reacts with B, we get C or something like that. There, these type of conditions will help us to identify the compounds. This is the previous slide, Shivangi. Okay. Halogenation means halogen will get attached on ortho or para. Friedel-Crafts alkylation means alkyl group will get attached on ortho or para. Acylation, acyl group will get attached on ortho and para. The important point here is that you need to remember in case of ethers halogenation, okay, aryl ethers halogenation, don't just use bromine, you have to use the acid also. In acid, bromine in acid. Conditions are very important in Friedel-Crafts reaction. Then last one, nitration. Again, the similar one, and you know that nitration does not take place by HNO3 only, rather in presence of H2SO4. So you mentioned H2SO4. It is actually first in the mechanism. The first step is by H2SO4, and then after that nitration takes place. And again, the same thing, NO2 group either gets attached on ortho or para. Para is major. Because this is anisole, you can say this one as ortho nitroanisole, this one as para nitroanisole. However, as per alkyl convention, methyl 2 nitrophenyl ether. Why? Because it is oxygen. Here you have CH3, and here you have, in this case, NO2. So this carbon is 1, this carbon is 2. So on one side you have methyl, and on other side you have 2 nitrophenyl. So this is methyl, this is 2 nitrophenyl. It is similar to what you say. For example, you have CH3, CH2O, CH3. This is methyl, this is ethyl. You say it is ethyl, methyl, ether. Similarly, here also, methyl 2 nitrophenyl ether. Alphabetical order. M comes first and then N, so that's why methyl first. Here, ethyl E comes first, that's why ethyl first. Any confusion, you can let me know. Now the question, write the reactions of Williamson synthesis of 2-ethoxy 3-methyl pentane is starting from ethanol and 3-methyl pentane 2-ol. Remember in Williamson synthesis, we talked about that uh, specific alkyl group will get attached to halide, the other one will form the ether. So why that is so? You need to remember, you need to recall all those. Means which halogen you should use, rather which haloalkane you should use. Okay. See here. In Williamson synthesis, an alkyl halide reacts with an alkoxide ion. It is an SN2 reaction. In the reaction, alkyl halide should be primary, least stringent. Hence, an alkyl halide is obtained from ethanol and alkoxide ion from 3-methyl pentanetol. Remember, it is not given that directly you need to use the alkoxide and the haloalkane. These are not given. You have to start with ethanol and 3-methyl pentanetol. It means you have to get those compounds first, and then you need to have Williamson synthesis to get the ether. Okay. So you need alkyl halide, and that should be primary, and then you should have alkoxide. So alkyl halide is obtained from ethanol. What you have ethanol and 3-methyl pentanetol, means you have CH3 CH2OH, and you have CH3 CH2 CH CH3 CH CH3. 1 2 3. On 3 you have methyl, and on 2 you have ol. Both are alcohols, but out of these you need to have one as alkyl halide. So alkyl halide should be primary, and the other one should be alkoxide, sodium alkoxide, for example. Okay. So with this knowledge that the alkyl halide should be primary, you should use primary alcohol to get alkyl halide. Okay. And you should use the other one to get the alkoxide. So get it reacted with sodium. Sodium will replace the hydrogen of the OH group, and you will get sodium alkoxide. Sodium alkoxide. This sodium alkoxide and these two will react with each other. Now, alkyl halide, primary alkyl halide, and sodium alkoxide will react. And as per Williamson synthesis, you will get ether. Sodium and bromine will form NaBr. The rest parts will get attached. To H5 will get attached here. Tell me if the concept is not clear. In Williamson synthesis, the alkyl halide should be primary. So you will use primary alcohol to get alkyl halide. You will use secondary alcohol to get sodium alkoxide. Then you will get the alkyl halide and sodium alkoxide reacted. The alkyl halide primary and the sodium alkoxide you will get reacted to get the ether. The actual Williamson synthesis is this part, in which you get alkyl halide reacted with alkoxide to get ether. Very important preparation method of ethers. Any confusion? Next question. Which of the following is an appropriate set of reactants for the preparation of 1-methoxy 4-nitrobenzene, and why? Tell me the answer in chat box. 1 methoxy, 4 nitrobenzene. Only two answers received till now. Two responses. I'm not saying answers. Okay. Good. Ashi, Preeta, Divya, all correct answers. Sohani also. Alkyl halide primary. Okay. So if I go back, here halide is 2 degree because this is attached to two carbons. Next, predict the products of the following reaction. Predict the products of following reaction. Reaction with acid halides. Reaction with acid halides. Okay. Okay. Yes. Arshi, correct. General rule I told you. Yes, Shivangi, but tell me the main product as well. Major organic product you should tell first. Mehak, that is a secondary product. Tell me the first product. Shivangi, Preeta, Mehak, correct. Okay. So cleavage as a thumb rule, if there is no tertiary, secondary, tertiary, the thumb rule is very simple. CO bond from the smaller group side, it will break. It will attack the hydrogen and bromine will attack this carbon. So propyl alcohol or propanol will be formed and bromomethane or methyl bromide will be formed. Next, predict the products of this reaction. Yastika, yes, correct. Of this reaction, this one is very easy. It is written Preetha products. So you need to write all, not just the major one or not just the organic compound. You need to write all. The answer is correct. Yeah. So here cleavage will take place from here. The reason is very simple. This is double bond character. And moreover, more hindrance. Cleavage will take place from here. Yes, Sohani, Preetha, Vanna, Shastra. Correct. Tell me product of this one. Concentrated H2SO4, concentrated HNO3. Yes, Ashi, correct. Shashwat, yes, correct. Don't give me formula. Just tell me what will happen. That will be sufficient. Just in plain English, tell me what will happen. Yes, nitration will happen, Mehak and Arohi, but at the same time, you need to say at ortho and para positions. NO2 group will get attached at ortho and para position. Para will be major. You have to write both because the question is products. Next, tell me the products of this reaction. Just as a hint, this is tertiary, this is primary. Hmm. Yes, Ashi, correct. I have already given the hint. You should be able to recall now that cleavage will take place at which theo bond because it is tertiary. So, Sohani, okay, correct. You mean tert. Probably might be autocorrection. Arohi, yes. Divya, no. Because it is tert, that's why the reaction mechanism will change. Shvangi, yes. Yes, correct. Good. So in this case, because this is tert, 3 degree, this carbocation, tertiary carbocation will be more stable. Is very stable. Hence, the reaction mechanism will be SN1. So tertiary carbocation will be formed, means CH3, CH3, CH3 plus, and hence the iodide I minus will get attached on this positive carbon. So third butyl iodide will be formed. Cleavage here will take place from here because there is tertiary alkyl group.